Swayam Prabha. Digital India. Educated India.
So, we will continue our discussion on denaturation. Last class we looked at some details of chemical denaturation. So, I will just briefly mention some of the mechanisms, or a few mechanistic insights that people have provided over how actually denaturation is brought about by, say, urea. Now, let me tell you this, whatever I am whatever sentences I am going to write, or you will be seeing on the slide, those are from very recent research papers. So, that means that no matter this denaturation, whether chemically, whether by urea or guanine hydrochloride, is so commonly used, but still there is a lot of discussion about how actually these two compounds bring about the denaturation of a protein or a peptide. There are two separate schools of thoughts like this, and you will try to appreciate that. One is that the denaturant directly interacts with the peptide backbone, okay, and opens it up. The other school of thought is that the chemical denaturant changes the structure of the water near the peptide and thereby bringing about denaturation. There are two different schools of thought, okay. But this is from a very recent paper, and what it says about urea denaturation is this. Look at the first sentence. Urea displaces water in the first solvation shell, FSS is the first solvation shell of the protein, and this arises from increased dispersion interactions, which means van der Waals interactions of urea with protein as compared to water. Now, this is we have not exactly looked at urea peptide interaction, but we know what van der Waals interactions are, and what it says is that urea just gives rise to more dispersive interactions as compared to water, right. That is number one. The next is there is an increase in the extent of protein backbone interactions, okay, with urea, leading to swelling of the protein. Subsequent to this, water penetrates the protein interior, right, and then the solubility of the hydrophobic groups undergoes enhancement in presence of urea. So, if you think about these three statements, you see these are very logical statements, right. This is the way you would think about a protein denaturing. One, it interacts with the protein directly, right, which is your backbone interaction. Two, it has more dispersive interaction. So, that means in the first solvation shell where you will be having water molecules, you replace those water molecules gradually by what? Urea, and that is thermodynamically favorable because why? Because the dispersive interactions of urea with the protein or peptide backbone is thermodynamically more favorable than that with water and the protein or peptide backbone. And the last one obviously makes sense, because remember when you are exposing proteins, that means you are unfolding proteins, you are exposing more and more hydrophobic groups, and you better have this thing that the hydrophobic groups are more soluble, because if they are not soluble in this urea solution, then they are going to fold back and form the folded structure again. So, intuitively thinking, these three do make logical sense, right. So, there have been a lot of computational studies. Theoretically, experimentally these things have been a little bit hard to prove, but still there are experimental studies, we will not go into that, but just keep this in mind about what sort of interactions or what sort of lines that people would think about when they try to look at the mechanistic insight of a denaturant, a chemical denaturant actually unfolding a protein. Okay. And you can see the reference at the bottom. This is a PNAS paper 2008, right. It is from Dave Thirumala's group at the University of Maryland, and they have been doing a lot of work with regards to this. Okay. Now, this is one thing I would like to tell you before I go further. See, if you would be doing chemical denaturation, that means unfolding a protein with help of urea guanine hydrochloride, how would you actually determine the concentration of the denaturant solution? Now, one way is the most straightforward way is you know what volume of sample you have, you know what concentration of denaturant you want, whether urea guanine or hydrochloride, and you weigh it out on analytical balance, right, and then dissolve the same amount in water and do the corresponding stuff. But the problem is, as you will see, the first sentence will tell you denaturants are often quite hygroscopic, hence determination of concentrations by the weighing method can be inaccurate, right. So, that means you take urea, but the actual amount of urea is less because you have more water adsorbed onto it. So, you are essentially you are overestimating the denaturant concentration. Now, why is this so important? Again, try to realize this. Suppose you have done a measurement, say on a certain week, on a certain day of the week, say on Monday, right, and that day the humidity level was not that high. Okay. Now, you are doing the same measurement, say on Thursday, when the humidity level is very high. Now, what will happen? The amount of water that is absorbed or adsorbed by this denaturant would be different. So, essentially on both these days your actual concentration based on your weighing out will be different, right, because you have different amounts of water adsorbed. So, what will happen is if you are trying to do a reproducibility, if you are trying to do a reproducibility, what will happen? Your experiments might not be reproducible because your actual concentration of urea, though by balance you have taken the same concentration, but because of the differential amounts of water adsorbed, your actual concentration of urea is different, right. So, if you ever see that, definitely you would think that that's must, that's something that must have happened. Okay. Then what do people do? People try an alternate thing. What they do is, it does not matter, okay, you weigh out something, you put it in the solution, you dissolve it in a buffer, right, and then you take the refractive index measurement. Because of the refractive index measurement you are taking in solution, right, it is not in a solid sample, and in solution mostly is water, so it does not matter. So, refractive index is actually going to tell you the concentration of urea, actual urea you have dissolved in water, right, and obviously there are relations. So, I will just give you the relations, we will not go into those derivations. So, you can see the concentration of urea is given by this expression, where you have the first term is a constant times delta n plus another constant of delta n square plus another constant of delta n cube. I will tell you what delta n is very soon, and then again the concentration of guanine hydrochloride is given by a very similar expression, right. And you can see what delta n is. Delta n is the increase in refractive index of the denaturant solution with respect to that of the buffer. That means what you do is you prepare your, say you are preparing denaturant concentrations from say 0 to 8 molar urea, right. Now, 0 molar urea is essentially what, your buffer. So, you take the refractive index measurement of your buffer, right, then you go to 1 molar urea, there will be a change in refractive index. So, that is your delta n, then again you go to 2 molar urea, delta n, and then you put it in this equation, and correspondingly that delta n will tell you what the concentration of urea is. Okay. This is how you do it, and this is the best way of doing it, because as I said, in our country where humidity levels differ a lot, in Delhi it is probably not a problem that that much of, because if you take in winter or say in the summer months it is essentially very dry. But if you go to a place like say Calcutta, where I am from, what will happen? The humidity levels are really high and they can really fluctuate, and there you will be running into a problem. So, it is best to create an alternate or to go by an alternate method, which is this refractive index measurement. Okay. So, if you are ever doing this, make sure you do that to cross check your measurement, because this is going to give you the actual concentration of urea all the time. Okay. So, the last topic would be pressure induced denaturation, but before I do that, before I actually do pressure induced denaturation, I will try to give you a small relationship between chemical denaturation and thermal denaturation. See, this is a very logical question that someone can ask or it can come to your mind. We have studied thermal denaturation, we have studied chemical denaturation, right? Both are denaturants, right? Both are going to denature the protein, but at any point of time, how are these two related? Because we are doing a denaturation, albeit by two different methods. One is you are providing thermal energy, the other one is providing a compound, which does something with the protein and denatures it. But what is, can we have a relationship between, say, the T, or between the denaturation concentration and the temperature at which your thermal melting is occurring? So what we are going to do is we are going to try to derive a very small relationship. So a relationship between thermal and chemical denaturation. Right. Now, before we start with the actual derivation, what we will do is we will just define two temperatures. One is Tu. What is Tu? Tu is the temperature. Tu is the temperature at which you are performing your urea denaturation experiment. Urea denaturation experiment, right? And see, we discussed this before, right? The difference between thermal and chemical is, thermal is you gradually change the temperature, chemical is you do not change the temperature. It is an isothermal transformation. Transformation in the sense it is done isothermally, you keep the temperature fixed and then you change the denaturation concentration. So that temperature we are taking as Tu. Okay. Now what we do is we define another temperature. Now this temperature, listen to carefully. I define Tb. What is Tb? Now first I will tell and then write it down. What Tb is, this is how I look at it. See, at Tu, at any given denaturation concentration, you will be having a certain structure of the protein, right? Depending upon what denaturation concentration you have. If it is low, it is more towards the native. If it is high, it is more towards unfolded state. If it is in between, then it is in the transition region. It will be a mixture of both. And we are always taking into account the fact that it is a two state, right? Native, unfolded or denatured. Now the way I define Tb is, remember I am trying to find a relationship. So the way I have to find a point of similarity between these. But what is my what should I say, scale of similarity? The scale of similarity would be that temperature or that something related to the structure. That means I chemically denature it at a certain concentration C at temperature Tu. I get a certain structure. So this is a certain structure. So to get a relation, I have to find another structure in my thermal denaturation profile at a certain temperature, which or where or at that point the structure is closest to the structure I have in urea. Is it clear or not? So that means I am trying to compare two different things. In chemical denaturation at a certain concentration C, I have a structure, right? If I am going to compare these two, I better have the same structure, and I say that I take a certain temperature, that temperature is Tb, where the structural similarity of my thermally denatured state is most to that of my chemically denatured state, right. So then in brief I can write Tb is that temperature of a thermal unfolding transition wherein the structure of the protein ensemble is closest to that obtained by urea denaturation, okay, by a certain concentration of urea, I mean by a certain concentration of urea at Tu, by a certain concentration of urea at Tu. Just go through the statement and see whether it is clear or not. Again it says Tb is that temperature of a thermal unfolding transition wherein the structure of the protein ensemble is closest to that obtained by a urea denaturation, where I am assuming a certain concentration of urea, say C, but done at Tu, because Tu we are not changing for chemical denaturation, right. So, this is a starting point. We have defined two different temperatures, right, Tu and Tb. So, we got to now think about this. What we can do? What we can do is, this is what we are going to do. Both these, at both these temperatures, you will be having delta G. Now, both these are structurally equivalent now, they are closest. So, the delta G should be the same, and I know my delta G dependence of thermal, I also know my delta G dependence of urea. So, what I would do is I will just equate these two, and that is essentially I am going to do. Okay. So, let us do that. So, from before we have seen that delta G, say from thermal as a function of temperature, say I write here Tu, okay, delta G Tu, well, yeah, okay, let me write Tb for the time being, because Tb is my thermal unfolding that temperature, is equal to delta Hm 1 minus Tb over T of m, okay, plus delta Cp Tb minus Tm minus Tb natural log Tb over T of m. So, what I have done here is, if you remember before, we did not have Tb, we had just T. So, delta G of T is equal to delta Hm, we know what m stands for, and we just had T. Now, we are saying is, we have defined this temperature Tb, and our reference temperature is Tm always, we have defined temperature Tb, and that is what we are just putting in, right. Okay. Now, from your chemical denaturation, what do you know? From your chemical denaturation, this is your thermal, right. From your chemical denaturation, what you know is delta G, okay. Delta G I can say as a function of a certain concentration of urea C at temperature Tu is equal to what? Is equal to delta G, remember it was H2O, right, minus m times C. What is C? C is the concentration of your urea or denaturant, isn't it? Okay. So, these things we know now. So, what I am going to say is that because I am looking at structural equivalence, right, then I can say that my delta G T of B should be equal to what? Delta G C T of U, okay. I can say let this be that. I can give these equations as this is number 1, the previous number 2, and this is number 3. So, you are clear up to this point, right. Now, if you look at delta G C T U, that C is taken care of by M C in equation 2, right. But what is delta G H2O? Delta G H2O is that free energy change where you have 0 denaturant. So, this now remember this experiment is done at Tu. So, what I can do is this for this delta G H2O, what I can do is I can take this delta G H2O, and in my original in my original relation where I have Tb is equal to T, I can replace that T by what? Tu, the same thing. Do you realize this? See, this is delta G H2O, right, at a specified temperature. My specified temperature is Tu, right. Now, what I also know is that delta G at any given temperature is by this relation. So, what I just do is, since I have already done Tb, I replace now Tb with Tu, that is it, because there is no denaturation concentration. So, then what I can do is I can write delta G Tu, I will just write it down, is equal to delta H m 1 minus Tu over T of m plus delta Cp, it will give me Tu minus Tm minus Tu natural log Tu over T of m, and this is say equation 4. Is it clear thus far what we did? Okay. Now, because based on equation 3, based on equation 3, that means this one where we have equated these two, okay, what can I say now? Now, this is what I can write down. Okay. I will go to the next page because this will not give me much space. Based on equation 3, this is what I can write. What I can write is delta H m 1 minus T b over T of m, then plus delta C p T b minus T m minus T b natural log T b over T of m is equal to, now equal to what? Is equal to delta H m 1 minus, now I should instead of T b I should be having what? T u, right, T of m plus delta C p T u minus T m minus T u natural log T u over T of m. Okay. But is this all? Minus m c, is not it? So, this should be minus m c, and this is equation number, what should the equation number be? Equation number 5, I guess. See equation number 5. Okay, right. So, we are trying to get a relationship between T b and T m, and if you are going to try get a rather T b and T u, and if you are going to try to get a relationship between that, we must make sure that it has a dependence on denaturation concentration, because depending upon the denaturation concentration your structure is going to change, is not it. So, we have to have the dependence. So, that is minus m c. So, then if I just cover this from here to here, this portion is delta G H2O done at temperature T u, right, and this is just m c, the free energy dependence linear. Okay. So, what we will do is now we try to simplify it. And the way you do it is we take m c to the left hand side and then bring the whole thing to the right hand side. Okay. And this is what we should be getting finally. Just correct me if I am writing anything by mistake. I can write then m c is equal to delta H m, then I can write T u minus T b over T of m. Is the first term okay? Then I can write delta C p, then it would be T u minus T b, okay, because T m and T m cancels, right. You can see the T m cancels. Now, what we are left with is, if I get, so let me get this again, if I get this minus T b natural log T b over T m on this side, it becomes what? Plus T b natural log T b over T m, right. But what I will do is I will change the logarithmic now, that means I will go to ln T m over T b. Okay. So, hence this one I can write as minus T b natural log T m over T of b. Okay. Then what would the next term be? Plus T u natural log T m over T of u. Okay. And let this be equation number 6. Which one? You are right, it would be T b minus T, is not it? You are absolutely right. Well, what I will do is this T b minus T. Thank you. Yeah, absolutely right. Okay. So this is the simplified form we have up till now. Now what we will do is, the problem is again we have this logarithmic term. We will try to linearize this equation. We will try to linearize this equation, and we assume for this one, what we assume is Tm by Tb and Tm by Tu are very close to 1. Very close to 1. Okay, Tm by Tb and Tm by Tu are very close to 1. That's what, see, that's the reason why we change this logarithmic division term. So now I will use another approximation. I will write down the approximation for you. So we will expand the natural log terms. We will expand the natural log terms, right, to get, and I can write this one down now, minus Tb natural log Tm over T of p plus Tu natural log Tm over T of u is equal to minus of Tb then Tm minus Tb over T of b plus Tu Tm minus Tu over T of u. Okay. Now, if you simplify this, what do we get? If you simplify this, what do we get? You see, Tb cancels, Tu cancels. What am I left with? What am I left with? Minus Tm plus Tb, then plus Tm minus Tu. So it is Tb minus Tu. Okay, and this one let this be equation number what? 7. Okay, so see, you have taken a complicated term, a series of terms or a combination of terms. You applied a linear approximation, right? You linearized it, and then you get a very simple term like this. So I can go forward and put 7 back in 6, I guess that is what it was, right. So then I can have MC is equal to delta Hm Tb minus Tu over T of m, then I should be having plus delta Cb Tb minus T of u. Right. So that is what we get. Now you can see the relation is very simple. We always were trying to get a relationship between what? Between Tu and Tb essentially, because Tu is where we are doing this unfolding and Tb is where the thermal unfolding transition where it was structural equivalent. Okay. So from here what should I be getting? I should be getting this is MC is equal to this, then I can write down, I will just give you the final form. Yes. Okay. Then let me write this down, Tb minus Tu, which was this one, I forgot this, then I can write plus Tu minus T of b, right. Yes, see, that is why I lose track of these big equations. Okay. So Tb minus Tu, Tu minus Tb, well, I get rid of this term totally, goes to 0. So therefore I have MC is equal to delta Hm Tb minus Tu over T of m. Okay. And therefore finally I can write down the last expression for you, then Tu is equal to T of b minus MC T of m over delta Hm. So this is equation 8, then this is my final equation. So you can see that means there is a very simple relationship, albeit under the condition, under the approximation that you are assuming a linear approximation, right. If you take higher orders, then obviously relation will be complicated, right, you will be having problems. But then what it says is Tu is equal to Tb minus Mc Tm over delta Hm. You know what Tb and Tu are, you have defined them. M is a slope, you can get from your free energy measurements. C is the concentration, you know, and delta Hm and Tm are also known to you from how we discussed about fitting your thermodynamics data, especially for thermal transition. Okay. Now, let me tell you this. Again, this we have derived using a linear approximation, but the problem is this equation only holds for low concentrations of denaturant. That means, when you are in the regime of say 1 to say 1 to like maybe 4 or 5 molar of denaturant, then this condition will hold or this equation will hold. If you go to very high concentration of denaturant, especially 7, 8 molar or even 9 molar urea, then you will see deviations from this linear relationship. The reason being, your linear approximation does not hold at the time. You have to bring in higher orders, and only after you bring in higher orders would you be able to model the actual relationship between Tu and Tb. Okay, so please keep this in mind. So this equation, so equation 9 is equation 9 valid for low concentrations of denaturant, right, deviates when concentration of urea or denaturant is greater than or equal to 6 molar, then deviations are observed. Okay. So, finally, we have come to a point where we have been able to derive through approximations an analytical relationship between Tu and Tb, and you would know, given a certain temperature Tu and a certain temperature Tb, how they would be related if we are talking about structural equivalence, because that is something we always have to keep in mind. Okay. We cannot talk about two different structures, because then the free energies would not be the same, the free energies have to be the same, hence we have to talk about the same structure. So, this brings us to the end of our discussion on chemical and thermal denaturation. I do not want to, well, you will see that there are many other variations, there are many other insights, there are many other models to it, especially for chemical denaturation. There is something known as a binding model, but you know, we will not go into that because the idea is not to look at the different models, but the idea is at least for you to be able to appreciate what all goes in when we look at interactions between say a thermal transition and a protein when you are putting in thermal energy, or a molecule which is able to denature your protein. Okay. And one thing you must have seen is, no matter what you do, in both the cases your accessible surface area plays a huge role, because accessible surface area determines your delta Cp, as delta Cp is very strongly related to accessible surface area, and you have also seen that your M is also related to your accessible surface area. So, M and delta Cp typically go hand in hand, because they are highly dependent upon your accessible surface area, and it only makes sense because the more you denature a protein, the more you increase the accessible surface area, because you are opening up the protein, and then the more you are opening up hydrophobic groups into the surrounding solvent. Hence, delta Cp does play a huge role no matter what you are talking about. Okay. Now, the last topic that we would be talking about in denaturation is pressure denaturation. Now, pressure denaturation, why would we care about that, or why did we not talk about it before? So, if you talk about pressure induced denaturation, so pressure induced denaturation is important. Why? So, number one, pressure is an important thermodynamic variable. Okay, so pressure is a very important thermodynamic variable, but whatever you have seen up till now is temperature. One was the thermal transition, because it is easy for you to do, and the next one was urea, at a specific concentration of or a specific temperature. Then why are pressure temperature or pressure experiments so rare? Because pressure dependent experiments are rare because of the complexity of experimental setup. So, everyone realizes that pressure is a very important variable, a very important thermodynamic variable, but the one that has been the bottleneck, or that has been the real obstacle is that if you would be trying to apply a huge amount of pressure, then the amount of the type of experimental setup you need would be kind of sophisticated in the sense that it should be able to withstand that amount of pressure, because you have to apply a pretty high pressure. I will tell you what the pressure is in approximate range, and that is why people did not want to invest so much time in it, because they were easily looking at denaturation through what, thermally or chemically. Okay. So, this was the main thing behind it, but nowadays with people trying to probe different things, taking on different varied topics, people have actually started looking at pressure denaturation, right, in details, though not so many groups, few select groups have actually started. Now, what is the other importance of pressure denaturation? The other importance of pressure denaturation is you can decouple effects arising from changes in volume, which is delta V, from effects influenced by thermal energy, right. That means, if you are applying pressure, then the direct effect would be what, in terms of volume, and if you have a temperature dependent experiment, what do you do? In temperature dependence, you not only increase the temperature, what do you also do? You also do expansion, or if you are going the other way, you do compression. So, in that case, the delta V change is also inherently involved, though we are not looking at it. So, what does pressure do? Pressure helps you separate the thermal energy component from the change in volume component. That is why again pressure is so important, but the fact is that these things are hard to do because of proper experimental setups, right. And as I was telling you, the pressure range we are interested in for proteins. So, the pressure range typical is from 0.5, let me write this again, 0.5 to 1 gigapascal. 0.5 to 1 gigapascal, okay, G stands for giga. Now, you can understand how high a pressure this is. Just normal pressure is not sufficient, you have to have pretty high amounts of pressure, and to have this you have to have a very dedicated experimental setup, and that is what people have not been able to do so frequently. It is one of the reasons, or that is the major reason. Now, if we are going to look at your free energy change because of both pressure and temperature, see, logically what should we have? Whatever delta G we have seen up till now, especially for thermal, it only includes temperature, right. So, somehow I would have to bring in a change in delta V, right, and if I am going to bring a change in delta V, then instead of measuring delta V directly, what I can do is I can do it by some other parameters. If you guys can recall, in thermodynamics there is alpha, coefficient of thermal expansion, and beta, remember isothermal compressibility. So, what are these? So, if we can somehow in delta G incorporate these two, then we can have a situation where I have information from both, from pressure dependent and from temperature dependent, and the temperature dependence plus volume I have from the thermal transition. So, somehow I can relate these two. Okay. So, let us try to do a small derivation. The reason I am doing this, I know these derivations take some time, but if you do it from the basic principle, you just have a better feel of it, right. So let us do that and let us see where we go with that. Okay. So what our starting point is, we know this, d of g is equal to, see, this is where we start from, a free energy. What is it equal to? Minus s dt then plus v dp, isn't it? Okay. So this one I will say is, I will start the equations again numbering. So this is 1 for me, this is under pressure denaturation. Okay. But we are not looking at g, what are we looking at? We are looking at delta g. So can we write as d of delta g is equal to minus delta s d of t plus delta v d of p, and this is something you know, right. Okay. Now what can we have? At transition temperature, you remember what the transition temperature was, like Tg, Tm, these are the transition temperatures. At the transition temperature, what about delta g? Delta g equal to 0. Okay, if you have delta g equal to 0, then what can we write? I can write delta s d of t is equal to delta v d of p, or I can write d of p over d of t is equal to what? Delta s over delta v, right, and this is equation 3. What equation is this? Clausius-Clapeyron equation. Okay. So I can write this as delta g is equal to 0. So this equation is your typically Clausius-Clapeyron equation. Okay. So these are 3 equations we start with, and nothing is new to you, right, these you know. Now what I will do now is, I will give you the final expression of delta g, what people have derived, or what we are going to derive at least to a certain part or to a certain extent, and then go about see to see how we can derive it. So I will give you the final expression. The final expression of delta g, is equal to delta beta by 2 p minus p0 squared. Okay, just write it down, I will explain it to you. Then plus delta alpha p minus p0 t minus t0, okay, then minus delta cp t natural log t over t naught minus 1 plus t naught, then plus delta v naught p minus p naught plus delta s naught t minus t naught plus delta g 0 or delta g naught. So just look at these. The first one has what? Beta. The second one has what? Alpha. So these are, this is alpha is your thermal expansion, the other one is your isothermal compressibility. The next one has delta Cp, right, this we had seen for your thermal transition. Then we have delta V0 because V naught rather, I will tell you what these are, P minus P naught, then delta S naught T minus T naught plus delta G naught. Okay. See, now you can realize this, the way we derived the thermal transition, we did dg is equal to minus s dt plus v dp, right, or d of delta g is equal to minus delta s dt plus delta v dp. When we derived the thermal, what did we say? We actually said that dp essentially was 0 because there was no pressure dependence. That was the assumption we took, and that is how we derived it. Okay, but you know when you are increasing temperature, you can play with pressure, right. So here what you are doing is you are integrating the full equation. So what do you do? How did we get this? So let me write this as equation 4. How to start to get this relationship? So how to start? What we start from is, we start from again d of delta g, the same thing, this is equation minus delta s dt plus delta V d of P. This was equation, I think what it was 2, right. It's equation 2, and we say we integrate this equation, using the limits T naught P naught to T P. Okay. We integrate this equation. What are the lower limits? T naught for temperature, P naught for pressure. What are the high limits? T for temperature, P for pressure. Again, because in this case we are not assuming anything, we are saying that free energy is dependent on both temperature and pressure. That is what GTP is, right. G depends upon temperature and pressure. Okay. So, let us try to see how we can do it. Okay. But remember this, can you integrate this equation just in a straightforward manner? That means, can I just integrate d of delta G and write delta S T minus T 0 plus delta V P minus P 0, can I write that? One thing is I am not going to get the equation I showed you, that is for true, but the thing is you cannot do that. Why? Because both this delta S and delta V would be having the dependence of the others. So, these are not independent, right. You cannot consider them to be independent of each other. Why? Because S is a function of what? P and T. V is also a function of P and T. So, hence we would have to take the variation of delta V or delta S as a function of these two variables. That is what we have to do first, and then we come back and plug it back into this equation and then do the rest. Is it clear? Because delta V and delta S are not independent of these, they are dependent on these variables we are changing, or the limits between which we are integrating, right. So, then what we now do is, this is also very simple and you guys all know what we say, that okay, let us look at delta V dP first, right. Let us look at delta V dP. When we are looking at delta V dP, what I am saying is, I am saying V is a function of P and T, right. I can straightforward say that, right. V is a function of P and T, okay, your P V is equal to nRT. And if I say that V is a function of P and T, and remember these are all functions which are what functions? State functions, they define the state of the system. So, I can write exact differentials of the state functions. If I can write exact differentials of the state functions, what should I write? For dV, this should be equal to del V over del T, then I can write at constant pressure d of T plus del V over del P at constant temperature d of P. Okay. So, this I would keep as what was the last equation number, do you remember? 4, was not it? I will keep as 5. But remember, we are not interested in V, like we were not interested in G, we were interested in what? Delta G. So, here we will be doing delta V. So, what I will just then do is d of delta V is equal to del of delta V over delta T P d of T plus del of delta V over delta P temperature d of P, and this is equation number 6. See, you already have a differential relation for delta V which is dependent upon what? T and P. That is what you wanted, because you know that they were delta V was dependent upon this, right. Now, we do a small change, I hope you will appreciate this. This d delta V I can rewrite as delta V, I can rewrite as delta alpha d of T, okay, plus delta beta d of P. Yes or no? See, the way you would define alpha is what? Remember the way you would define alpha? 1 by V, then del V by del T at constant pressure. But you know what? Why you take 1 by V? What was the reason you take 1 by V? There is a reason. Is alpha or beta and beta intensive or extensive? Intensive properties. How do you make it intensive? By dividing by V, right. That is why you have the V, like 1 by V times this is actually alpha. You know, that is why in that sense I should not be calling this alpha, but I am trying to tell you, if you take 1 by V, it is say Vm essentially is a V molar volume. You say that expansion per unit volume. That means you can never have an extensive variable now. You already have, like it's per mole, right? When you define per mole, it's no longer extensive, it is intensive. The same thing I have done here. Is it clear? That's why you are not taking 1 by V here. So now if I have this now, remember our delta V is depend upon temperature and pressure. So what I can do is I can integrate, I can do d of delta V between what limits? T naught, P naught, T P, isn't it? And this should now should give me now what? Now this is only a function of temperature. I can write delta alpha dt T naught to T plus delta beta, then this is dP, this should be what? P naught to P d of P, okay. Or I can rewrite as, now check this, I can write delta V T P minus delta V T naught P naught, okay. I have clumped them into one, is equal to, what is my first term? Taking into consideration the fact that delta alpha and delta beta are constants, okay, they are not varying, they should be delta alpha T minus T naught, then what do I have? I should be having plus delta beta P naught. So let this be equation 8, okay. And the way I can rewrite is, what I'll do is I'll make a small change. What I'll make a small change is I'll use delta V T naught P naught to be delta V naught. It's like a delta G naught, right? It's your delta V naught at a certain temperature, okay. So then this would change as delta V T P, okay, is equal to delta alpha T minus T naught plus delta beta P minus P naught, then what I have is plus delta V naught, which is equation number 9. Is it clear? See, we started from very first principles and we just took into account the dependence of delta V on T and P. Now you think about this, if you go to the original equation, that means if you go to the original equation which we had to start with, look at this original equation. If we are going to integrate now d delta G between what? T naught P naught to T and P, you already have an expression for delta V which you have just derived. This delta V naught depends upon what? It depends upon T, which is T minus T0, it depends on P, the P minus B0, and then there is one constant term which is delta V naught. So you can just, instead of delta V, you can just put that in, right, and integrate that portion out, okay. This is for you to do, right, and for you to do. But one thing you can realize, if you go back to your previous equation, the very first equation that I wrote down, I said I will come back to it, this equation number 4, look at this. You already have an expression with delta beta coming from delta V, you already have something which is P minus P naught, okay. Look at the second term, you already have delta alpha from delta V, because these are relative volume changes, isn't it? Then you already have T minus T naught, okay. The P minus P naught is missing, but you know, if you would do delta alpha dP, T minus T0 is a constant, then you will get P minus P0, okay. Then the rest we do not have, except we have delta V naught. Delta V naught is also already there, okay. So keep this in mind, so this is important. Now what about the other one? What was the other one? The other one was, let us try the other component of d delta G. Okay. That means, now what we are going to try is, we are going to try delta S dt. Okay. We are going to try delta S dt. I am omitting the negative sign now, we will put in the negative sign later. Okay. Now, it is delta S dt. Again, what do we start with? We start with S is equal to a function of S, right, or a function of Pt, right, and again all these are exact, I mean state functions, exact differentials valid. So, I can write d of S is equal to del S over del P T at constant pressure d of T plus del S over del P at constant temperature d of P, and let this be equation 10. But we are not interested in S, we are interested in what? Delta S. Then d of delta S is equal to del of del S over del T at constant pressure d of T plus del of delta S over delta P at constant temperature d of P. Just let me finish this one. This is 11. Okay. Now, what I can write for this one? For example, this first term, what can I write? I can write d of delta S is equal to delta Cp by T d of T. Okay. And this one I can write as minus delta alpha d of P. Okay. I will tell you where I am coming from. So, let this be equation 12. Where am I coming from? I am coming from this. Remember there was something referred to as Maxwell's relations. Okay. So, delta V by delta T at constant pressure, let me put in a, well, delta V, let me put in, at constant pressure would be del of delta S by delta P at constant T. Okay. And you know already that this one is alpha. So, this one is what? Delta alpha, we already know that, and hence you get equation number 12. Okay. So, this is based on Maxwell's relations. Please go back and check. Right now, what I just do is, just let me do this because I am almost to the end. I integrate equation 12 limits T naught P naught to T P, and what do I get? I get delta S T P minus delta S T naught P naught, okay, is equal to delta C P dt over T T naught to T minus delta alpha dP P naught to P. Okay. I am integrating equation 12 just like that, and let me write down the final form before I end the class. Up till this you are okay, right? You just integrate it, that is it, nothing more. Then I can write delta S T P minus delta S naught, okay, this is like same like delta V naught, is equal to, taking delta C to be a Cp to be constant, I can write delta Cp natural log T over T naught minus delta alpha P minus P naught, right, and this would be equation 13. And lastly, then delta S T P is equal to delta Cp natural log T over T naught minus delta alpha P minus P naught plus delta S naught, is equation 14, where delta S naught is equal to delta S T naught P naught. Okay. I know I have run out of time, but this is what I had to complete today. because otherwise I would have to start afresh the next class. But you can see by doing this, again you have delta S, where you have the other remaining terms. One was delta Cp, which you already have, right? Well, delta alpha you already had, and the other one is delta S naught. Okay, these things have come in. So what you now do is you take this, put it back into the d of delta G is equal to the delta S dt minus delta S dt plus delta V dp. Replace delta S and delta V by the these expressions like equation 14, and what was the other equation, I forgot, equation 9, yeah, 14 and 9, and you should be getting the final expression of delta G, okay, which has both volume changes and also temperature changes. That is the most general equation you can derive. Okay.